Hi everyone, today let's look at a classic problem, longest substring without repeating characters. Opening. The problem gives us a string and asks for the length of the longest contiguous piece of that string where no character appears, more than once. For example, in the string spelled A, B, C, A, B, C, B, B, the answer is 3 because the slice A, B, C has all different characters. We need to return just the length, not the slice itself, and a substring must be contiguous, not a subsequence with gaps. Naive approach. A first idea is to try every starting position and every ending position, and for each candidate check whether it has any repeated character. This is correct, but it is slow. There are roughly n² candidate slices, and checking each one can take up to n steps. So the worst case grows like n³. We would like something much faster. Core idea. The key insight is to use a sliding window that only ever holds characters with no repeats. We keep 2 pointers, a left end and a right end, and we grow the window by moving the right end forward 1 step at a time. The window always represents a valid substring with no duplicate characters. When we read a new character on the right, one of 2 things happens. Either the new character is not yet in the window, so we simply grow and the window stays valid. Or the new character already sits somewhere inside the window, which would create a duplicate. In that case, we cannot keep the old occurrence, so we jump the left end past it to the position right after the previous occurrence. To find the previous occurrence instantly, we keep a hash map that records the most recent index of every character we have seen. Key details. There are 2 subtle points worth highlighting. First, we do not shrink the left end 1 step at a time. We jump it directly to 1 past the previous occurrence of the duplicate, which makes the whole scan run in a single pass. Second, the hash map remembers positions from earlier windows too, not only the current window. So when we look up a character, we must also check that its remembered position is still inside the current window, meaning it is at or beyond the left end. If the remembered position is before the left end, it belongs to an old window and is no longer relevant. So we treat the character as new. After every step, we update the map with the character's current position, and we record the current window length against the best length found so far. Walkthrough. Let's trace the first example using the string spelled A, B, C, A, B, C, B, B. We start with an empty hash map, the left end at position 0, and the best length set to 0. The right end moves to position 0 and reads the letter A. The map is empty, so there is no conflict, and the window is free to grow. We record the letter A at position 0 in the map, remembering its latest occurrence. The current window runs from position 0 to position 0, so its length is 1. The best length rises from 0 to 1, and the best window is now the single letter A. The right end moves to position 1 and reads the letter B. The map holds only A, so B is new, and the window keeps growing. We record the letter B at position 1 in the map. The window now spans positions 0 through 1, giving a length of 2. The best length rises from 1 to 2, and the best window is now A, B. The right end moves to position 2 and reads the letter C. The map holds A and B, so C is new, and the window keeps growing. We record the letter C at position 2 in the map. The window now spans positions 0 through 2, giving a length of 3. The best length rises from 2 to 3, and the best window is now A, B, C. The right end moves to position 3 and reads the letter A. The map already holds A at position 0, and that position is at or beyond the left end, so this is a duplicate. We jump the left end to 1 past the previous occurrence, which is position 0 plus 1 equal to 1. The old A at position 0 is skipped in a single hop. We update the map so the letter A now points to position 3. The current window runs from position 1 to position 3, giving a length of 3. The best length stays at 3, since this does not beat the previous best. The right end moves to position 4 and reads the letter B. The map holds B at position 1, and that position is at or beyond the left end. So this is a duplicate. We jump the left end to 1 past the previous occurrence, which is position 1 plus 1 equal to 2. The old B at position 1 is skipped in a single hop. We update the map so the letter B now points to position 4. The current window runs from position 2 to position 4, giving a length of 3. The best length stays at 3. The right end moves to position 5 and reads the letter C. The map holds C at position 2, and that position is at or beyond the left end. So this is a duplicate. We jump the left end to 1 past the previous occurrence, which is position 2 plus 1 equal to 3. The old C at position 2 is skipped in a single hop. We update the map so the letter C now points to position 5. The current window runs from position 3 to position 5, giving a length of 3. The best length stays at 3. The right end moves to position 6 and reads the letter B. The map holds B at position 4, and that position is at or beyond the left end. So this is a duplicate. We jump the left end to 1 past the previous occurrence, which is position 4 plus 1, equal to 5. The old B at position 4 is skipped in a single hop. We update the map so the letter B now points to position 6. The current window runs from position 5 to position 6, giving a length of 2. The best length stays at 3. The right end moves to position 7 and reads the letter B. The map holds B at position 6, and that position is at or beyond the left end. So this is a duplicate. We jump the left end to 1 past the previous occurrence, which is position 6 plus 1, equal to 7. The old B at position 6 is skipped in a single hop. We update the map so the letter B now points to position 7. The current window has collapsed to the single position 7, giving a length of 1. The best length stays at 3. The scan is complete. The longest substring without repeating characters is A, B, C, with a length of 3, so we return 3. Complexity. The running time is linear, proportional to the length of the string. The right end moves forward once across the whole string, and the left end only ever jumps forward, never backward. So together they do, at most, 2 passes of work. Each hash map lookup and update is constant time. The space is linear in the size of the character set, since the map stores at most 1 entry per distinct character. Summary. The sliding window turns this problem into a single left-to-right scan. The 2 ideas to remember are the hash map that remembers each character's most recent position, and the rule for jumping the left end directly past a duplicate instead of shrinking 1 step at a time. The check that the remembered position is still inside the current window is what keeps the map core wrecked across many windows. Together, these give a clean, linear time solution. Thanks for watching, and see you next time.